All right, so we just talked about this theorem 4.3. And for the next exercise, you're going to use theorem 4.3. This idea of if you have a series of a bunch of things added together or subtracted, you can take the calculate the limits individually, right? This is basically like the sum a sub n plus minus sum b sub n, and then find those limits individually. And you're going to apply that to exercise 9. One part of it might be a little, well, the whole thing's kind of tricky, but try it out and see what you get. If you get stuck, unpause the video and I will explain how to do it. Okay, so the idea for this one is we're going to basically break it up into 3 series. One of these is 1 over n squared plus n. I'm going to factor out that n because that's going to be useful to us. And then I'm going to write the sum. This one right here, I'm going to break it up into a 3 over 7 to the n. And that's going to be a minus 5 to the n over 7 to the n. So 3 over 7 to the n and 5 to the n over 7 to the n. And the last 2 of these are kind of obviously, or maybe not completely obviously, but they're geometric series. And the third one, the 1 over n times n plus 1, that's the one that's particularly tricky. So let's do each of these separately. I'll start with this one over here. Whoa, that line got all crazy. I'll start with this one over here. So I can rewrite this as 5 over 7 to the n, starting at n equals 1 to infinity. And this is pretty clearly a geometric series. The question is just what's a and what's r. So my a is just going to be my first term. So if I plug in n equals 1, I'm going to get 5 over 7 to the 1. So a is 5 over 7. And r, the thing that I'm multiplying by each time, is also 5 over 7 because that's what I keep increasing the exponent by. So that is going to converge because 5 over 7 is less than 1. And it converges to a divided by 1 minus r. So that's 5 over 7 over 1 minus 5/7. That gets me to 5 over 7. Let's see, this will become a 2/7. And when I multiply by the reciprocal, I'll get a 7 over 2. The 7's cancel. That one's 2.5. All right, how about this middle one? Do this one here. So I'm going to write this. I'm going to take the 3 and put it out in front. And then I'm going to write it as a 1 over 7 to the n. And again, this is n equals 1 to infinity. And if I plug in n equals 1, I'm going to get 1/7, and I'll get that times 3. So this means that my a is 3/7, and my r is just 1/7, because that's what I'm multiplying by each time that I raise the exponent. So this is going to be equal to 3 over 7 divided by 1 minus 1 over 7. That's going to be a 3/7. This is going to become a 6 over 7, and when I multiply by the reciprocal, that's 7 over 6. The 7's cancel. This just gets me to 3 over 6, which is 1/2. All right, and now we get to this first one, which is a particularly tricky one. And one way of doing this is just sort of writing out the terms and seeing if I can figure out what's going on. So it's going to be like 1/2 plus 1/6 plus, I said plug in 3, I get 1/12 plus When I plug in 4, I get 1 over 20. So this seems to be decreasing relatively, the size of each term decreasing relatively quickly, but it's really not clear what it's going to. If I started actually adding them up, it's like, I think it's 1/2, and then when you add the 1/6 to that, you get 4/6, which is 2/3. When I add 1/12 to that, I'm getting, let's see, this would be 8/12 plus 1/12 would be 9/12, which is 3/4. And then when I add the 1 over 20, this is 15 over 20 plus 1 is 16 over 20, which is 4/5. So when I add up each of these partial sums and I look at the pattern there, it looks like I'm just getting n over n plus 1. And that is clearly going to converge to 1 as n goes to infinity. But it's not clear how I'm supposed to do that. So what I'm going to do is I'm actually going to use a trick that we've seen before. Oh, I just zoomed in. Which is I'm going to rewrite this fraction using partial fractions. And it's going to end up coming out to being 1 over n minus 1 over n plus 1. And that's not too hard to see. Like if I did my a over n plus b over n plus 1, I know those are the factors there. And then I cross multiply, I get an plus a plus bn all over n times n plus 1. And I know I want the a plus b to equal 0 because there's no n term on top. And the a just has to equal 1 because that's my only constant term there. So then you immediately get that b equals -1 and the whole thing sort of falls out. And what happens when you actually start plugging things in here? I plug in n equals 1 and I get 1 over 1 minus 1 over 2. And then I'm adding to that when I plug in n equals 2, 1 over 2 minus 1 over 3. I plug in n equals 3 and I get 1 over 3 minus 1 over 4. And you can see where that goes. And now what happens is the 1/2s cancel, the 1/3s cancel, and then the 1/4 is going to cancel because I'll get a 1/4 here, and everything will cancel all the way along. So you're going to end up getting a 1 minus, well, really, I should say it this way. You're getting the limit as n goes to infinity of a 1 minus 1 over n plus 1. And this thing just ends up going to 0. So this whole thing here ends up summing to 0, which is exactly what we thought we were getting over here. So adding that all up, that's 1. Sorry, this is supposed to be a minus here. My apologies. 1 plus 1/2 minus 2/2. 1 plus 0.5 minus 2.5. My final answer there is -1. So this thing that happened in this example right here, there's actually a name for it. It's called a telescoping series. And these are series where certain terms will cancel out terms before them. So that allows us to figure out that things converge and what they converge to. So this one that we already saw, when I rewrote it as two separate fractions, I saw that when I started writing out the terms that things would cancel each other out, and I just end up with like the first term minus the last term. And the trick to this is figuring out, first of all, that something is a telescoping series, which isn't always completely obvious. And then you write out the first few terms to figure out what's going to be canceled out, and then you use that to figure out the partial sum. So let me do an example that's a little bit strange. Here, it's not necessarily obvious that this is going to be a telescoping series, but often with series, if you're kind of confused, it's sometimes good to just write out the first few terms. So this would be arctan of 1 minus arctan of 2 plus arctan of 2, if I'm now plugging in k equals 2, minus arctan of, 3. And now if I plug in k equals 3, I get arctan of 3 minus arctan of 4. And that's going to keep going. And hopefully what you'll notice is that the arctan of 2's are going to cancel. The arctan of 3's are going to cancel. The arctan of 4 is going to cancel. And your, so this is calculating my S sub n. All right, everything's going to cancel except the very last term way out here, which is like our arctan of n plus 1. Because I haven't added the next term yet, so I haven't canceled that one out. So this is going to turn into an arctan of 1 minus, this should be a minus here, arctan of n plus 1. So that's what each of my partial sums is going to be, because all the stuff in the middle is going to cancel out. I'll just get the first term and the last term. And the question is, what is the limit as n goes to infinity of that partial sum? Well, arctan of 1 is just a, that's just a calculation. So what is arctan of 1? You get tangent of something equals 1 when you're at like the 45 degrees, because that's when you're getting the sine and cosine values the same. So this right here is just going to turn into a pi over 4. And then the limit as n goes to infinity of arctan of n plus 1. To figure that out, we actually need to just graph the arctan function. And this is a good one to throw into Maple. Or if you just remember, arctangent looks like that. And it has 2 horizontal asymptotes. One of them is at pi over 2 and the other is at negative pi over 2. So as n goes to infinity, we're going out here. This thing right here is turning into a pi over 2. And the reason for that is that as you get closer and closer to pi over 2, think about tangent of pi over 2. That's sine of pi over 2 divided by cosine of pi over 2. What's happening is sine of pi over 2 is getting closer and closer to 1, and cosine of pi over 2 is getting closer and closer to 0. So this thing, 1 divided by 0, that's heading towards infinity. So if I'm doing the arctangent as something heads to infinity, my value is going to be that expression right there. In any case, you get a pi over 4 minus a pi over 2 as your answer, which is a negative pi over 4. All right, so go ahead and try to use this concept of the telescoping series to see if you can figure out exercise 11. Ready, set, go. Pause the video if you haven't already. Work on it, and then come back. All right, so for this one, there's a couple tricks. First one, it starts at n equals 2, and the reason for that is because you're doing an n minus 1. So if we started at n equals 1 or n equals 0, we'd be getting a 0 in the denominator, which would be bad. So let's just write a few of these terms out. At n equals 2, I'm getting 1 over 1 minus 1 over 4. At n equals 3, I'm getting 1 over 2 minus 1 over 5. At n equals 4, I'm getting 1 over 3 minus 1 over 6. At n equals 5, I'm getting 1 over 4 minus 1 over 7. At n equals 6, I'm getting 1 over 5 minus 1 over 8. And at n equals 7, I'm getting 1 over 6 minus 1 over 9. and that's going to keep going. So I'm following my hint here. I wrote out the first 7 terms of the partial sum. And this is really, I guess, let's just call this S sub 7, which is really only the first 6 terms because I started at n equals 2, but whatever. And see what terms are canceling out. So what is canceling out? Oh, this 1/4 here is going to cancel with my negative 1/4. This 1/5 will cancel with that 1/5. This 1/6 is going to cancel with that 1/6. And I think that's it. Let's just put in one more here to see what's going on. This is going to be a 1/7 minus 1/10. Oh, and then this 1/7 is going to cancel with that 1/7. And then my next one that I write out, I'll get a 1/8, which will cancel with that one. So this S sub 7, I'm getting 1 plus 1/2 plus 1/3, and then I'm getting like a minus 1/8, minus 1/9, minus 1/10. These first 3 terms here will never get canceled out, because I didn't start canceling out until I got to this 1/4, right? Which was canceling out this negative here. But I'm just canceling out those negative terms each time as I go along. And these first 3, the 1, the 1/2, and the 1/3, they're never going to have something come up to knock them out. These things, though, will get canceled out as I add more terms. But there's always going to be sort of 3 things on the tail end. So what is this going to look like? My S sub n, it's going to be like 1 plus 1/2 plus 1/3 minus, let's see, this 1/8, this is when I had like n equals 8. So this is going to be like 1 over n minus 1 over n plus 1 minus 1 over n plus 2. And what's the limit as n goes to infinity of that thing right there? Well, let me erase this. The 1, the 1/2, and the 1/3 are going to stay the same. And then I'm going to subtract, well, I'll say the limit as n goes to infinity of a negative 1 over n minus 1 over n plus 1 minus 1 over n plus 2. And each of these individual pieces, well, they all just go to 0, right? This tail end here, the 1 over 8 minus 1 over 9 minus 1 over 10, as you get to larger and larger n values, that's just going to keep getting smaller and smaller, and the first 3 terms are going to stay the same. So we end up just getting the 1 plus the 1/2 plus the 1/3, which ends up being 11 over 6, or 1 5/6. And this stuff all just goes to 0. All right, go ahead and try exercise 12 if you have not already. Pause the video now, work that one out, and then unpause it when you are done. All right, so exercise 12, when we start writing this out, when we do n equals 1, we get the cube root of 2 minus the cube root of 1. At n equals 2, we're getting the cube root of 3 minus the cube root of 2. At n equals 3, we're getting the cube root of 4 minus the cube root of 3. And it's pretty easy to see what's happening here. That cube root of 2 gets canceled. This cube root of 3 gets canceled. And it's going to keep going. So this was like my S sub 3. So in general, S sub n is going to be a negative cube root of 1 plus the cube root of n plus 1. And what happens, the limit as n goes to infinity of, this is just going to be a negative 1, because the cube root of 1 is just 1. plus the cube root of n plus 1. Well, as n goes to infinity, if I'm doing the cube root of like 1,000, that's just going to get bigger and bigger. So this thing, this telescoping series, diverges. It's just going to get bigger and bigger as you keep adding on more and more terms. And that's the end of that.